All right, let's get right into it. The whole AI revolution, right? With these incredible models like GPT-4 and Gemini, it feels like they run on pure magic, on data and algorithms. But it turns out there's a surprisingly physical and absolutely immense resource powering it all: electricity. And I mean, there's no question about it. These frontier AI models are changing everything. They're transforming science, medicine, how we work, you name it. But this whole digital revolution is being powered by something we just kind of take for granted. It's not just code floating in the cloud, it is a constant, massive, and very real flow of power being pulled from the grid. So that brings us to the real question here. What is the actual energy price tag for one of these massive AI models? The answer? Well, it's pretty staggering. To really wrap our heads around this, we're going to break down the energy cost of probably the most famous model out there, OpenAI's GPT-4. Okay, so let's start with the sheer hardware. To train GPT-4, it's estimated they used about 25,000 of NVIDIA's A100 GPUs, and they had them all running for about 3 months straight. Now, each one of those chips can pull up to 400 watts, so you can probably imagine how fast this starts to add up. And why on earth do you need that much hardware? Well, because the scale of the computation is almost impossible to comprehend. GPT-4 is thought to have somewhere around 1.7 trillion parameters. Those are all the little knobs the model tunes as it learns, and it was trained on a dataset of 13 trillion tokens. The number of calculations is just mind-bending. So you can't just plug in 25,000 GPUs and press go. The real trick, the real challenge, is getting all of them to work together like a single coordinated brain. How do you even do that? This is a fantastic analogy for what's going on. Imagine trying to get 25,000 chefs to cook one single giant meal. You can't have them all stirring the same pot, right? It'd be chaos. You need a system, a way to coordinate all of them. In supercomputing, they call this parallelism. So to manage all this complexity, engineers use this really clever three-layered strategy. First, at the very bottom, they split single math problems across a handful of GPUs. Then they assign different layers of the AI model to different groups of those GPUs. And finally, to just chew through data at insane speeds, they make hundreds of copies of the entire model. Let's break that down. So that first layer, tensor parallelism, think of it like the head chef telling a small team, you guys are on veggie chopping duty. This all happens inside a single server, where a technology called NVLink lets 8 GPUs talk to each other so fast that they can work together on one huge calculation, basically acting like one giant, powerful chip. Okay, the second layer is called pipeline parallelism, and this is like the assembly line in the kitchen. GPT-4 has about 120 layers in its neural network. So what engineers do is create a pipeline of servers, where the output from one group, say the veggie choppers, gets passed to the next group, the sauce makers. All in all, it takes about 120 GPUs working in perfect sync just to create one cooking line for the entire GPT-4 model. Right, so, wait a second, that's 120 GPUs accounted for. But what are the other 24,880 GPUs doing? Are they on a coffee break? No way. This is where that third layer comes in. And this is the final, absolutely massive step: data parallelism. What they do is they take that whole 120 GPU assembly line and they just copy and paste it about 200 times. Each of these 200 kitchens gets a different piece of that giant data set to learn from at the exact same time. Then, an algorithm averages out what all 200 copies learned. That's how you put a 25,000 GPU farm to work. It's incredible. So now that we kind of get the insane scale of all this, we can finally talk about the energy bill. And I'll give you a little spoiler, that huge training run we just walked through, yeah, that's only the start of the story. So if you do the math, you factor in all the servers, how much power they draw, and that 90-day training time, you land at an estimated 44 gigawatt hours. That's 44 million kilowatt hours. It's a number so big, it's actually hard to picture. So to put that into perspective for you, 44 gigawatt hours is about the same amount of electricity that a small city with like 50,000 people would use in an entire month. All of that juice, just to train one model. But here is the real kicker. This is the part that most people miss. Training is a huge, but it's a one-time cost. The real energy hog is actually running the model every single day for millions of us. That's a process called inference.
For that same 90-day period, just serving up answers to ChatGPT users is estimated to have used 67 gigawatt-hours. That is over 50% more than it took to create the thing in the first place. The real energy drain is in the day-to-day use.
And believe it or not, we're still not done. All of those GPUs generate a ridiculous amount of heat. Data centers have this metric called power usage effectiveness, or PUE. A PUE of 1.2, which is actually very good, means for every watt of power you use for computing, you need another zero point 0.2 watts just to cool everything down. So all those gigawatt-hour numbers we just talked about, the real-world figures are actually 20% higher. So when you add all of this up, the training, the inference, the cooling, you start to see this trend emerge. And when you zoom out and look at the whole country, the numbers become truly alarming. Back in 2023, data centers already used over 4% of all U.S. electricity. With this AI boom, some projections say that number could more than double to 8 or even 10% by 2030. That's creating a hunger for power like we've never seen before. And this exploding demand has kicked off a brand new kind of global race. Because, at the end of the day, the most advanced algorithm in the world is totally useless if you don't have anywhere to plug it in. This has become a flat-out race for power. In the US, you can see this race being led by the tech giants themselves. They are not waiting for the national grid to catch up. They are taking matters into their own hands, buying their own power plants, planning these multi-gigawatt supercomputers. Meta is even building its own natural gas plants just to make sure they have enough energy. And this sets up a really fascinating contrast when you look at China. While the US approach is this kind of scrappy company-by-company race that gets slowed down by permits and lawsuits, China's approach is totally centralized and state-led. Their government can fast-track gigantic energy projects, solar farms, new nuclear reactors, you name it. And that could give them a major strategic advantage in an energy arms race where speed and scale are everything. Now, to be fair, this isn't just a brute force problem. Energy is obviously a critical piece of the puzzle, but it's not the only piece. There's constant innovation happening in more efficient chips, smarter model designs, better training methods, and all that stuff can help bring the energy costs down. The problem is, even with all those efficiencies, our overall demand for AI is just growing so fast that the total power consumption is still expected to shoot way up. And that leaves us with a pretty fundamental question about the future. The global race for AI supremacy is definitely on. We always think it's going to be one with the cleverest code or the biggest data sets. But as the demand for electricity just continues to skyrocket, you have to start wondering, will the future of AI ultimately be decided by algorithms or by who can build the biggest power plants?